Throughout the beginning part of this semester, we're going to try to have representatives from the various student organizations come in and introduce themselves and introduce the clubs so that you guys, who are mostly freshmen here, can get a feel for what types of extracurricular activities you can get involved with, some of which are fairly professional related and others are a little bit more fun oriented. But our first visitors today is somewhat impromptu. The Society for Women's Engineers, Women Engineering or Women's Engineering? They can introduce themselves, but this was impromptu. We're going to have them give more details when they come back in a week or two. So here we go.
All right. Hi, guys. I'm Jen Anderson, president of SWE. I'm just here to announce our evening with industry. It's next Monday night at 5:30. We have about 13 companies coming, and of those companies, we have Round Mountain, GE, Electrotherm, EE Tech, Navair, Sherwin-Williams, NV Energy, CH2M Hill, AMEC, Bally, Tri-Sage, Navy will be there. Basically what the event is, if any of you have ever been to Spring Celebration, it's like that, but much more low-key. You can go and network with the companies, sit down with them for dinner, try and get an internship. So we encourage you guys to dress business casual, bring a resume, and it's a lot of fun. You should come. And this is Jackie, our secretary.
Hi guys. So if you are interested in coming, tickets for students are $15. They're for sale in SEM 132 from Sam DeMuzio. You probably get emails from her, but we hope to see you guys there. It's great for networking, possibly getting an internship, meeting companies, and getting your name out there. So, yeah, that's it.
And also, one more announcement for ASCE. The president he's over there, actually, if you want to say hi. And they have a meeting tomorrow at 4 in SEM 234. They have, what? Oh, well, it's the American Society of Civil Engineers, if you don't know that. And they're having a meeting tomorrow at 4, SEM 234, free Jimmy John's, and they're having a guest speaker. So go to that too.
SEM 234 at 4, you said? Okay, thank you. So, I'm a little bit behind in trying to get the various student organizations to come in and visit with you, but the aim is to try to get them to introduce themselves early in the semester so that you guys can start attending meetings. So if you're a civil engineering student, I strongly recommend trying to attend that tomorrow afternoon, 4 o'clock, in SEM 230 something. Anyone know? 232? I'll send out an announcement today to everyone via web campus so you can get us the details there as well. So we'll have them come back probably in a week or two, and they'll have a little bit more time to introduce themselves. So let's get started here. So this here was just a test question. We're having some trouble still with the clickers in the other classroom, so we'll hopefully sort those out soon, though. Okay, some quick reminders as we get started. We have had a lot of teams come in and pick up their rental kits, but a lot more teams haven't yet. There's no real rush. You're going to have your kits in about 2 weeks. It's probably not a bad idea to take care of this as soon as you can. $50, you pay that to the cashier's office. Remember, like you did for the textbook rental form, you bring that over there. They'll take your money, they'll stamp your form, and they'll sign it. You bring to us the stamped and signed form, either to me after class or straight over to the EDL, and you can hand it in over there, and we'll get that entered into the system. Please try to take care of that in the next couple weeks, because if you don't, you're going to be missing some key things that you need for one of your skills lab assignments. We're handing them out as part of the rental kits. We're handing out the parts as part of the rental kits. Your team journals. Your teams should be meeting by now. Hopefully you've met more than once, multiple times. Your journals should be submitted starting this week. We have a form on the website. The front page of the form describes pretty much how we're going to grade it. So I'd read that front page pretty carefully. You can see how many points we're going to give for which types of answers we get. And then the second and third pages are actually information that you fill in, and everything from how much work you spent as a team on various aspects, what the project goals were for your week, what your individual tasks were, who was taking care of them, all that kind of stuff. Now, one of the things that Dr. Volstead mentioned last class is that one of the key things we see in this form is the percent contribution of each of the team members. And we realized we didn't really explain that fully. We are not looking, in fact, it looks very suspicious if every week you have a team of 5, if every week you have 20% contribution from everybody. We know that in the real world it doesn't work that way. If you have 3 exams this week, maybe your teammates can pick up the load for you in exchange for you promising to do a little bit more next week. This is what we expect to see on your teammate contribution form on a week-by-week basis. So if we see that every week, in and out, everyone's putting in exactly equal work, we generally think that is BS, and we're probably going to talk to the team because we know it never works that way in the real world. Try to be as accurate as you can. If somebody is putting in extra work, I expect the rest of their teammates to give them the credit for that, and maybe give them a week off next week or whatever. Okay, similar to this, the first CAPME teammate evaluation survey is going to be due next Monday. Here, this is anonymous. Your team journals, you give each other primarily a nod by saying how much work they put in terms of the percentage of the overall work. The CAPME survey is anonymous to each other. Your teammates don't see each other. How well your teammates rate you in your CAPME doesn't affect the grade. Whether you fill out the evaluations of your teammates at all, you get points for. Okay? So just to be clear here, the CAPME is worth 5 points each week, but that is for filling out the form accurately or honestly. You can be rated the best teammate in the world in the CAPME. That's not going to get you any more points or any less points if you don't. So please be honest. Now, the idea behind the CAPME, I think we've mentioned several times, is that it helps us identify the teams that are working very well together and those that have some problems. Maybe they aren't able to get together, the schedules aren't matching each other, or maybe you've had a teammate vanish, or somebody who's disruptive at your team meetings, or something to that effect. These things can happen. Try to give feedback in the CAPME survey to this effect, and we, as well as your TAs, will do our best to try to smooth out any differences that teammates might have, to recognize teams that are actually working pretty well as well. So, 2 things. In this last thing, in 2 weeks, you're going to have your second self-learning module. This one's important, probably more important than the lifting fan one, because if you don't get 100% on this one, it's the safety quiz, you can't actually finish the semester, right? Because you're going to be doing some soldering, you're going to be working with some hazardous materials, some might say flammable materials at least, with the hydrogen. You have to know how to work with these things safely, and it's not rocket science. Well, I guess it is. Hydrogen's used as a rocket fuel, but it's not hard, but you do have to get 100%, and it shouldn't be too tough. If you review the materials that we have there, most people get 100% in either their first or second shot. You can take that quiz as many times as you want, but unless you finish it and get that 100%, we can't let you work in the EDL. We can't let you work on any of the projects that involve soldering or hydrogen, and which basically means you can't work on the hovercraft project. So we don't technically throw you out of the class, but you're not eligible for about 75% of the points in the whole semester. So everyone does it. I don't want to scare people. Everyone gets this taken care of, but I recommend you do it as soon as possible, certainly before the deadline of October 1st. Any questions about that? It's all online. Closely related to this, you're going to have to get yourself some safety glasses before you start doing these things. The typical, you don't need like the chemical goggles you use in your chemistry classes. Just a simple, if you have polycarbonate lenses on your eyeglasses, that's fine. You can also pick up for maybe $2 at Home Depot the typical eyeglasses you'd wear if you're using a saw or a drill. They don't really have to be high-tech goggles or gas masks or anything like that. Okay. Good news for your engineering students. The Design News, which is a trade magazine, polled 122,000 students and found that engineering students study the most. It's good news, right? You're in good company. You have serious classmates who spend a lot of effort. All right, maybe it's not good for some people. Okay, a couple clicker questions to get started. Last class, Dr. Volstead covered a lot of the electrical engineering stuff. Raise your hand quickly if you did our recommended review of last class's notes before you came in today. Oh, gosh. Oh, that's sad. All right, well, okay. I'm seeing some hands. If your hand's up, good job. If your hand's not, well, now you can pay the price. All right, let's get this started. So the question is, which of these can it be? Not necessarily for this class, but what could it be? This falls under the category of common misconceptions. Okay, so the correct answer is a lift fan. Now let me talk about this for a second. Okay? The choices we have here are a battery, a lift fan, a fuel cell, any of the above, or none of the above. Now I guess technically you could literally plug any of those into the circuit. It just wouldn't work, or you might actually damage things. So no lawyer answers. Yes, you could plug these things in. But when we see a circuit drawn like this, on the left-hand side we have a power source where we have the polarities typically given. And Dr. Volstead covered this. This is commonly going to be a battery in this class. It also could be a fuel cell, because we're going to be talking about fuel cells later on. We didn't really cover that here. We're going to talk about fuel cells, and we're going to use them essentially as if they were a battery. We're going to take the battery out, and we're going to put the fuel cell in its place. Okay? Commonly, when you see this zigzag squiggle line, that typically represents a resistor in an electrical circuit. If you haven't seen that yet, you probably haven't had Physics 2 yet, or something equivalent, and you'll definitely get it in an electrical engineering course. We use the term R because it has some characteristic resistance. That's just what we call it. In plain language, it is the load on the electrical circuit. It is the thing that is being powered. Commonly, it's a motor. It can be an electromagnet, it could be a light bulb, anything that is drawing the electricity out of the power source. Okay? So in our case here, we use R because it has a resistance to it. But in reality, what we're talking about in this case here is a lift fan. Fuel cells and batteries are effectively the same thing, and that would refer to the stuff on the left-hand side over here of our schematic. Very simple schematic. In the real world, your schematics are usually much messier. Is there a question here? Okay, the question is, could you have as a resistor a charging battery? Technically, yes. However, that would be a little bit more complicated in that the overall circuit wouldn't be represented this way. Okay? We wouldn't call it simply a resistor. Okay? Like I said, that is correct, but I think in the spirit of what we have here, you can't say any of the above and you can't say none of the above, so it would still have to break down to that. Okay. Good question. Okay. Some of you have a fairly advanced familiarity with electrical circuits, and that's great. But I know that in a class like this, not everybody does, so questions like this might be a little bit difficult. If you haven't, and if you didn't review your notes from last class. All right. Okay. All right. Sort of just discussed that already. Next question. For the circuit shown, and pay attention to how it's drawn here. Okay. We have a fan. This is a centrifugal fan of the variety attached to a battery with this circuit. As the circuit is drawn there, what is going to be the voltage if you were to measure it across the fan? You don't need a calculator. You shouldn't need a calculator. All right. Well, we have a little bit more disagreement in the class about what the right answer is here. Okay. Again, this is the kind of thing that you'd probably be able to get if you looked at the notes from last class a little bit more carefully. Now, pay attention here. The switch is open. Okay? All right. It's a trick question. It's a trick question. But when the switch is open, there's no electricity flowing. So the voltage across your battery, yeah, that's still 12 volts. But the motor isn't seeing any voltage. Okay? So most of you answered 0, but a lot of you answered 12 volts. Had we closed the switch, everyone who said 2 would have been correct. Okay? Question? I didn't hear that. If you changed your answer halfway through, the system should actually accept the most recent answer. I'm pretty sure how the software is set up. Right? If you didn't get that right, check in the grade system afterwards and talk to me. It means I need to learn how to use the software better. Okay. Your teams hopefully have been meeting for a few times so far this semester, and hopefully you've begun some of these steps. We've shown this slide several points during the semester, and this is the design process as looked at from an engineer. Identify the problem or the market or whatever, including specifications and constraints. Who has actually read the specifications for the hovercraft? Not many. They're posted on the website. Right? They're posted right in the week 1 lecture materials. I just this afternoon added it to the week 2, week 3, week 4 lecture materials. Go in and check it. It's a 1-page description of the official rules for the hovercraft competition. If you have any questions about it, please come and see me or one of the TAs. But you want to look at the rules at the beginning of your process, right? You don't want to go 6 weeks into the semester or 3 months into the semester and then realize that you weren't paying close enough attention to one of the aspects of the rules and something you're doing is going to be called illegal once you show up to actually compete. Okay? Take a look at these rules, at these specifications. Gathering information, exploring alternative solutions. This brainstorming part is really where I expect to see most of the teams right now. Okay? If you've narrowed down your design, it means you're either way ahead of everybody and you've learned how to do all the calculations already, or you're jumping the gun. You haven't had enough opportunity to let ideas stew over in your head. So, different approaches to a hovercraft, different ways of generating lift, different ways of generating propulsion. If you're that far along, that means that you're reading ahead in the book because we haven't even come close to talking about fuel cells and propulsion. That's what we're going to talk about in a few minutes today. But the brainstorming phase is really one of the most important steps of the design process. Closely tied to it are the analysis and selecting a solution. That's where you consider your 5 or 10 ideas that you come up with in brainstorming, and you start applying the calculations, you start getting a little bit more rigorous to see whether the idea that looked good on the back of a napkin looks good after you've done all the calculations and you've convinced yourself that it will actually keep on working. And you might decide that in the analysis process that you need to do some more brainstorming because your calculations say it's not going to work or it's going to be too expensive or something like that. So you should be somewhere in this step up here, maybe still in the gathering information. Frankly, you'll be gathering information every time you do analysis as well. Okay, so please try to look at it in this framework. In a few weeks, you're going to start with your detailed analysis, and then as soon as you get your preliminary approval from the instructors, namely that your calculations are correct and you're not about to spend $200 on the wrong stuff. At that point, we're going to give you the go-ahead where you can start buying things to build and test your solutions, your detailed design, building and testing your solution. So typically, engineers don't do a detailed design for all 10 of their brainstormed ideas. That's not usually a good use of effort. Try to narrow it down. If it's a really complicated system, you might do a full design on 2 or 3 things, and then after you've seen it all built and tested, then you pick which one you're actually going to sell. In the real world, usually you make your decisions a little bit earlier on and narrow it down as much as possible earlier on, because prototyping, designing, and building 3 things is obviously 3 times more expensive than 1 thing. Okay, so we've talked about most of these, but we haven't talked about fuel cells yet. But the lifting fans, the deck plenum chamber, control units, and things like that, and the batteries that power it all, don't really give us a lot of insight into the details of how you're going to make this hovercraft go, right? See, step 1 is you got to get it to lift up off the ground. Step 2, it's got to go. Step 3, it's got to come back. And all this has to happen with no humans actually doing the actual control. It's got to be autonomous, all right? So the control part of this is very important. We're going to be doing the control using a Lego NXT. For those of you who have Lego Mindstorms, it's essentially one of those. This is actually it's a fairly powerful microcomputer inside this. They put it in a rugged case that a 3-year-old can throw against the wall and not have it break. But generally, it's much more powerful than incoming students think, well, we're playing with toys, you know. So how am I going to explain this to mom and dad? Well, I guess you are playing with a toy, but it's actually a fairly sophisticated microprocessor inside this that you guys are going to be programming, not using the kids programming language that comes with the Legos. You're going to be using LabVIEW, which is a full-up technical programming language that has interface, that has a library of commands that allows it to control one of these. So we'll be doing that later this semester. So you will become experts at some level of how to control your hovercraft using a microprocessor. Question in the back. RoboLab is the old stuff, yeah. Okay, the question is the new software going to be free? The software that will allow you to control and program this is already installed in all of the ECC computers. However, a $20 student version is available. I think we actually posted, when I talked about the free Windows and all that other software, I think the LabVIEW was listed there. If it's not, I'll make sure I add it in. We are currently talking to the bookstore here on campus to try to have them sell the student version of LabVIEW for $20. We're still in negotiations, or actually they're negotiating with the company that makes the software. If that doesn't work, you'll have to buy it online if you want your own copy. But it's only 20 bucks, and that's for, again, a student version of what is otherwise a typically multi-$1,000 software package. If you're a mechanical engineer, you're going to be using LabVIEW a lot starting in the spring. So if you're a mechanical engineer, you probably find it a useful investment to shell out 20 bucks for the software. But you don't have to. All of the ECC computers have it installed on them. Okay, so good question. Well, we're going to be talking about the LabVIEW stuff a lot more in a few weeks. Question? The question is, are you required to use LabVIEW? And the answer is yes. Yep. There are other programming languages, for those of you who are familiar with Mindstorms, that work with these Legos, but we're requiring LabVIEW. We don't want to have to teach and grade multiple languages. That's too much of a complexity. Okay, so today's main topic is the propulsion side, and we can also call it the navigation side of things. So lifting fans get you hovering. Propulsion makes it start moving sideways down the course. All right? The navigation is sort of a brief word that we can use to describe the process of sensing where you are on the board, on the playing field, and making decisions about what you want to do. Like, for example, now we're getting close to the end, it's time to start slowing down and reversing direction, or it's time to come to a complete stop. Those types of things we refer to as the navigation process here. And you need a brain in which to do that. We'll talk about that in a later class, but controlling hovercrafts is actually a fairly complicated thing. Here's a little YouTube video. Hope I'm not violating anyone's copyrights this time. Really? So that's just a leaf blower sticking into a hole in the bottom of a piece of plywood with a small skirt attached to the bottom. Now, they're probably high school students, because I don't think a college student would try this on a hill the first time. No elbow pads, no helmet, nothing. Probably private school. If that were public school, someone would get sued. So, it's not easy to control. I mean, he had problems just staying balanced, for one. But the process of manipulating what direction the hovercraft is going to move in can be done a lot of different ways. There are easy ways and there are not so easy ways. One thing I want to start off with is to gauge your mechanical intuition, we'll call it, your physical intuition. Here's a clicker question. If you have a hovercraft that has a weight that's initially in the center and you were to move it to the side, if the weight is in the center, I'll just give you, it's going to just hover there. If you balanced it well, it's not going to move sideways, it's just going to hover. But if the weight is moved to the side, what do you expect is going to happen? All right? We haven't talked about this yet. This is a clicker question aimed to gauge your physical intuition of what you think is going to happen. All right, 7 seconds. All right, where'd the answers go? There we go. Left. Most of you think it'll go left, some think right, some think nowhere. Okay, the answer is left. Okay. I think I can convince you in a moment. So consider, first of all, the case where you have a balanced situation, where the mass is right in the middle in such a case, you lift it up off the ground, but that the air that's being pushed below from the fan or whatever is squeaking out each of the sides, the left and right side, approximately equally, all right, if that's the case. So the airflow coming out the left and right is approximately equal. However, if the weight is shifted to the side, we're going to have the hovercraft tilt a little bit, all right? And again, we're not deriving the complicated fluid mechanics equations behind this, trying to gauge your intuition of the process. It's going to tilt, all right? And if it tilts, you're pinching off the air that would otherwise be trying to come out the left a little bit, forcing all of the air that's coming through the fan. Only a little bit's going through here. Much more is now going out through the right-hand side. And this sort of acts like a little bit of a jet, not literally as a jet, but it has the effect of more momentum. If you've studied momentum flow in a physics class, more momentum is going to go out the right, causing the reaction of the system, right, F equals ma. The reaction of the system is to move it towards the left, okay? This is a very useful way to steer a hovercraft, all right? You can make mechanisms that shift weights around on the deck of your hovercraft pretty well, pretty easily, okay? It's not necessarily the best, okay? There's lots of other ways to do it. This is one approach that, frankly, you can do it with a fairly small amount of energy, to simply slide a mass around on the top, okay? So this requires a mechanism by which you move this weight around. Right? So you would need to have, for example, the weights attached to a pulley and a clothesline, and you have a motor that reels it in, or a screw or something like that causes the weight to move left or right. I don't know. You guys can be as creative as you want. Or you can use a completely different approach, which I'll get to in a little bit. Actually, right here. There are a number of ways to try to take advantage of other things that don't involve weight shifting on the hovercraft that can cause a net motion in a sideways direction. For example, if you already know that you're going to have a fan blowing downwards to generate lift, maybe you can figure out some way that will harness this fan energy and shoot it, like, for example, a vane of some sort that will direct more of the air this way than goes in the other direction. Okay? That's one mechanism. However, we are very quickly going to run into one of the rules that we have here, that whatever is happening, the propulsion has to either be powered by or controlled by the fuel cell. Okay? Meaning that the fuel cell has to be an integral part of your system. Here I'm being a lawyer here. We're going to be very particular about how we enforce this. If we were to take the fuel cell out of your design, it can't work. Right? It has to be an integral part. You can't just have it there as dead weight, for example. Okay? It has to be actually doing something in a way that's meaningful. And our judge, we will be the judge of what actually is meaningful in this process. So here, if you have a vane that you wanted to switch between directing the air to the right, and then you maybe rotate this so that it's directing air to the left, the rotation of this vane would have to be powered or controlled by the fuel cell. That would be how we would say you could do this legally. All right? Another approach, maybe you open up little vents so that you bleed off air on one side that might cause the amount of air exiting out here to drop a little bit. Or maybe you actually can create enough of a jet so that it actually causes this whole thing to squirt that way when you have a little bit of air escaping here. The opening and closing of this window would have to be powered by the fuel cell. Okay? Technically, you're using the fan, the airflow created by the main lift fans, which are being powered by your main batteries, but the fuel cell is playing an integral role in your propulsion. It wouldn't be controlling, it wouldn't be moving sideways if you didn't have the fuel cell opening this little window. Okay? Other approaches. Some people might have multiple fans. Well, here the fans are oriented vertically, and they just have some ducting where the air flows in here and it gets redirected downwards underneath it. You could put a door that's, a sliding door or whatever, some kind of a mechanism that blocks off flow to one of your fans. But again, this mechanism would have to be powered by or controlled through, usually powered by, a fuel cell in this kind of a situation. So there are lots of ways you can use your fuel cell. You're not likely to be able to actually have the fuel cell do the main powering of a fan. I'll show you a picture of that in a second. You can use a lift fan that you mount on top of another rotating platform where the fan, not your whole hovercraft, just the fan points in different directions. When I showed you that short video clip of the U.S. Marines hovercraft, that's how they do their steering. They've got little vents that they look like little straws pointing up and then pointing sideways. They just rotate them around and it shoots out the air in a particular direction, and they can steer by pointing that forwards, reverse, left, and right. okay? You might be able to rig up some kind of a mechanism to do that in this class. This is the one that I was getting at a second ago. The auxiliary fan, you might have your main lift fan pointing straight down, that's all great. Then you buy a little small fan. A big fan has no hope of working. Maybe you can get it to work with a small fan. And you power this fan by a fuel cell, and that fan is just pointing straight out the back or maybe in the forward. Maybe if you want to steer left and right, you could do that too. You might be able to have a fan that is small enough that your fuel cell can actually do a good job of powering it. This would be a legal use of the fuel cell with a fan. Okay? Any questions about these various interpretations? You probably need some time to stew it over in your head in the next few weeks. Yes? Because so the question was, are you allowed to have your hovercraft drive forward to the other end and then have the whole hovercraft turn around? To have the hovercraft stop? Okay, so you would stop, which would cause it to sink back down to the ground, rotate your fan, and then have it come back to the other way. Technically, no, because you're touching the ground midway during your run. Okay. It would work for the first 3 or 4 checkpoints, but you would fail the final. Because for the final, you have to do the whole course there and back. For the first 4, you only have to go there. Okay. Good question. These types of things are covered in the rules online. Another question. Yes, if you have an auxiliary fan and you want to use rudders or something like that, those rudders, similarly to what we had before with these things, the rudder would have to be powered and controlled by the fuel cell. Okay. Controlled by the Lego NXT, but powered by the fuel cell. Question up front. But the fan doesn't have to be. The auxiliary fan could be battery powered. Exactly. Our interpretation there is that this fan might be giving you sideways thrust, but if we see any effective motion where your fuel cell was actually unplugged or your fuel cell wasn't there and it does the same thing as if it was there, we'll know that it wasn't integral. All right? So we'll actually be hands-on testing it to make sure that that fuel cell is doing something meaningful. Okay? So if you have a rudder, if you design your hovercraft well, you can go in a straight line with no problem. You don't need a rudder. Okay? So telling me that you have a rudder that's powered by a fuel cell when you don't even need a rudder, that might not pass our criteria. It has to be an integral part of your process. Question up front. So what are the milliamps and voltage of the fuel cells? You will study this and measure it directly yourself in one of the skills labs. Typically, the fuel cells, it's not at one number. The fuel cells here will max out at 3 volts, a total of about 1 watt when you're powering it with air. If you're powering it with pure oxygen, you can get more current and more power. But you actually will develop a curve that shows you when you're drawing this much current, it'll generate this much voltage, and it varies. How much current you get varies almost linearly with how much load you have on it. Okay, but I can't answer it specifically. You will be actually measuring that in a skills lab. Is there another one over somewhere in here? Yeah, okay. Okay, so the question was if you have an auxiliary fan that is powered by the battery but switched on and off with the fuel cell. The answer is that is not enough because the fuel cell doesn't really play an integral role in that process. Generally we want to see some sort of actuation, some sort of action, physical action with that. Okay, but good question. I'm glad. It shows that you guys are already brainstorming. Another one out back. Okay. So the question was, could you have an auxiliary fan mounted onto a servo where the servo is powered by the fuel cell? That would be okay, yes. Yep. So in other words, you don't have to use a vane or a rudder. You could actually move the whole fan around. But the motor that the fan gets rotated with would have to be fuel cell powered. Wow. Can you only use one fuel cell? Most likely. Fuel cells are $170 each. It's got to be in your budget. And actually, the fuel cell that we rent you is part of your rental kit, and we're only charging you $50 for that entire kit. All right? If you wanted a second fuel cell, if you wanted to buy it yourself, you'd have to use fair market value. None of this, my roommate gave it to me for 1 cent. Right? You have to use fair market value on all components in your budget. If somebody gave you batteries free from last year, you've got to give us the fair market value. By that I mean the brand new value, not the what it would go for on eBay if you got a really good deal. Right? So we're trying to make the playing field moderately level for everybody. Okay, I'm going to move on. If you have questions, you can ask me later on, but in the interest of time, I'm going to keep moving on. Now, there are other ways to power it, and it occurred to me after I made this that most jet engines involve internal combustion, which is not allowed. This is a jet engine, but you could have some jets powered by non-combustion processes, like water jets and things like that, air jets. Okay? But if you have any questions about what's legal or illegal for your propulsion mechanism, talk with me or Dr. Volstead, and we'll try to get you approvals or declines as soon as possible. Okay, the fuel cell. This is the size of the fuel cell. It's a big, big picture up there. This is the fuel cell. We're going to be handing these out in about 2, maybe 3 weeks in Skills Lab when you make all the measurements of its property. Okay? Whatever the propulsion technique you use, it's got to be controlled by the fuel cell or powered, which is I probably should change this word. Controlled/powered. Again, the fundamental criteria we're going to use is that it has to be an integral component, meaning it's got to be meaningful there, okay? And just some heads up, it is probably not going to be powerful enough to run most fans. You can find some fans that it will power, but you will have to decide whether it is enough to actually do anything useful with, right? If you can get the fan to barely rotate, that might not be useful for you, okay? 3 volts, 1 watt are the typical limits. You're not likely to get 3 volts unless you're powering something that's using almost no current. In reality, you're probably going to be getting closer to 1.5 to 2 volts for most stuff that you realistically are going to power. Okay. We'll talk more about fuel cells at length later on, but just so that you can get your brainstorming started, I encourage you to think of a fuel cell like a battery, okay? In that as long as there is hydrogen and oxygen going into it, it's going to be generating voltage, okay? And if it's in an electrical circuit, that voltage will be leading to electrical current flowing through the circuit. All right? So you can think of it as a battery. And you don't just turn it off by removing the oxygen or hydrogen. Well, I shouldn't say that. You could turn it off by removing the hydrogen or the oxygen. That's just usually not the easiest way to do it. We're probably going to be turning it on and off using our Legos, okay, with a relay, an electrical relay that I'll talk with you in a moment. It's just an electrically operated switch is what a relay is. That's what you can think of it as. So the fuel cell doesn't generate a lot of electricity. You can use it to power small motors, maybe release a small electromagnet, or, I don't know, light a light bulb if you can get propulsion out of a light bulb. Who knows? One clever approach that we give a little bit of a hint. In the old days, we never gave a hint, but no one actually realized you could do this. So now we're trying to plant some seeds for creative people. You can use a capacitor. You can buy a supercapacitor, they call them, or even ultracapacitors, that essentially acts as a small battery that can be charged very quick. But the benefit is that for, say, 30 seconds worth of charging from the fuel cell, you might be able to generate enough of an electric jolt and store it in that capacitor to run a motor for 10 seconds. It won't run for 2 minutes. But if all you need is to move a rudder or something like that, 10 seconds might be just fine. If you want to learn more about how to use a supercapacitor, you can Google it. You'll find all sorts of things. People can make all sorts of neat things with supercapacitors. You can buy them for $5 or $10 from the companies that you'll be buying your other stuff from. If you're interested in this, come and see me during my office hours, Monday, Wednesday, Friday at lunchtime. Some of the TAs might know how to do this. We haven't told them yet. We haven't trained them yet. But I recommend coming to see me as opposed to other people until we get them trained on how to do these things. Okay. Recall our circuits from last Monday. We have 2 main things that we're probably going to be concerned about making an electrical circuit for in this project. The lifting fans, which have to be attached to a battery. Lifting fans should each be, remember, R's represent in our projects, there's typically going to be fans. There might be other things. R is a fan. If you have multiple fans, you want to put those in series or in parallel. What's this? Series or parallel? Parallel, good. Here, it helps that I drew them parallel to each other, right? They're not always going to be drawn that way, but put them in parallel. That way they both see the same voltage coming off the battery. If you have a 12-volt battery, both fans will see 12 volts, and they'll run at the same speed and the design speed. All right. The fuel cell circuit tends to be much simpler. Because you're only going to have one fuel cell, odds are you can't fit a second one into your budget. You're only going to have one fuel cell. your circuit looks almost the same as this, except you're in parallel with nothing. Right? So it's just one. Fairly straightforward circuit. So the trick is going to be how we actually control these things. So in this class, you're not allowed to have control, you're not allowed to touch or interact with your hovercraft once it starts, essentially, once our clock starts on your contest. You are allowed to have like a master switch to allow you to disconnect your batteries from everything else, right? But once you push the on button on your hovercraft at the start line, which then causes it to lift up off the ground and do its thing, once you push that button, there's no more interaction allowed. So you will probably have an on switch, first of all. I strongly, in fact, we're even probably going to require that you have an on-off switch, because the alternative is to be there yanking the cables to unplug your batteries continuously, and you're probably going to be breaking your batteries frequently. The cables, they're not meant to handle that much stress. So a simple on-off switch. I think we even give you one in your rental kit for free. So basic circuit. You have a motor, for example, over here. Notice I'm no longer drawing it with the squiggles of a resistor with an R. Now I'm actually going to draw it as a motor. Motors usually have a black wire and a red wire, and many of them have other wires too. You have to figure out which ones you care about. DC motors will have a black wire and a red wire. If it has other wires, those are usually for speed sensors that you don't need to use in this class. You would need a lot of electronics to actually understand what that signal is. But you'll have a black wire and a red wire. Motors will work in both directions. You can plug your negative on the battery into the red wire of your motor, the positive side, or the other one. All that's going to happen is what? It's going to go the other way. Okay? So if you plug your motor in backwards, you shouldn't see any of the magic smoke, right? If you hook up your electronics to the battery and you see smoke, it no longer works, right? So it's magic. The electronics are all magic black boxes. If you let the magic smoke out, it no longer works. Okay, so if you let the magic smoke out with a motor, it means that you're trying, because you can hook it up backwards and not have to worry about it. You'll just have it rotate. The fan will rotate in the wrong direction. It won't lift your fan off the ground. It'll suck it down into the ground. Okay? It's good if you want brakes, but you're not allowed to touch the ground in this competition except at the start-finish line. Question? Question, does the NXT have the ability to switch polarity? The answer is no. Okay? But I'll be talking about that in a second. A workaround for that. It's even worse than you think. Okay, so this is just a circuit that we're not controlling. One second. This is a circuit that we're not controlling, right? In order to have some control in here, we need a mechanism by which to turn the motor on and off. As written now, the motor is just going to be turning because it's attached to the battery, right? So we're going to attach a switch in there. In this class, you have manual switches that people can operate, but you're going to want switches that get triggered by your NXT, okay? This is essentially a switch that is electrically triggered by an electrical signal coming out of your NXT. So in order for that to happen, we actually need to use a special kind of a switch called a relay, and I'll talk about this in 1 second. But did we have a question over here? Yes. 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 So the question was, are you allowed to go to the far end, turn around, come back, and then suck down to the ground once you get to the finish line so that you don't fly off the end of the board and you get maximum points? The answer is yes. You don't actually have to reverse it. You can probably just turn it off so that there's no lift. But that's the only place you are allowed to touch the ground is when you are behind the start-finish line. Okay? The question, could you use your master switch to turn it off at the finish line? The answer is no. No, only at the start line. All right, you're being a lawyer on me. It's important. These are good questions, and I really do encourage creativity, but I'm not trying to make it ridiculously easy for people. Then everyone does that, and we defeat the purpose of using sensors. All right? So manual switches would be drawn something like this. When we want to use an electrically operated switch, we call this a relay, and this is going to be another little cube. You'll be getting a couple of them in your rental kits. We call it a relay. Inside of the relay, it's got a little switch, but the switch is actually attached to a little electromagnet, where if you power the electromagnet, the switch moves in one direction. You use little magnets, and it sucks the switch in one direction, and you turn it off, and it goes in the other direction. It'll either be passing the electricity through one path or the other path, depending on what direction that electromagnet is powered in. Okay? It's a fairly clever little device. They've been around forever, but they're very effective. So the electrical circuit in this situation still has our battery, still has our motor, but the switch that we had here is now replaced by this switch inside of your relay that has to be ultimately controlled by energy coming out of your NXT. Okay? And again, all this is doing is turning the power on and off. It is not reversing the direction of the polarity, the positives and negatives. All right? It's only turning it on and off. Okay? In order to actually reverse the polarity, which would mean having the positive of one go in one direction and the negative going another direction, and then switch to switch, and the positives and negatives both get reversed, there you need what's called a double pole switch. Usually we find double pole, double throw switches, but double pole actually is what we would need. We're giving you double pole, double throw switches in it. In this case here, you have two possible paths for the electricity to flow. So out here we have some kind of a motor or something like that. You have your battery. And this switch can have two positions. Either it goes to this top path or it goes flowing through the bottom path. Okay? Pretty useful. Now, how can we use this with a motor? Well, imagine that we had a motor that we wanted to reverse directions. We have a relay thrown in here, and the relay is set up so that both sides of the relay, we're switching two things simultaneously. Okay? We're going to switch the positive side of our battery's wires and the negative sides of the battery's wires. Each one of these has two possible paths through which electricity could flow. So in this configuration of the relay, the electricity, the electrons will flow along this top path, which means the positive side gets routed to the positive side of the motor. Okay? And the negative side, and I'm just following which ones are connected here, the negative side gets routed to the negative side of the motor. We have the positive side of the motor over here is also connected to this side of the relay, but it's just left there floating. There's nothing actually attaching to it over here. Okay? So if we were to then switch the relay, switch the switch, in the other direction, so that instead of the path going out the top of the relay, it now goes to the bottom, now the positive side is routed, now it goes down here to this side of the motor. Okay? What this effectively will do is switch the direction of the motor. The same thing's happening with the negative side of the battery. The negative side of the battery no longer goes down this path. It's now going down this bottom path, up and around, goes in the opposite side of the motor. Okay? This is a clever way by which you can use a relay that essentially has one control signal. It says, flip the switch. In one position, the switch has the positive going on one side and the negative going on the other side. Flip the switch, and then they just get reversed. They each go to the opposite sides. But you're switching two things simultaneously in order to make this happen. Okay? This is how you can use this with a Lego NXT, where you can actually reverse the direction of the motor. So in this project, we're going to actually have to cause the motion, come up with a mechanism by which we create propulsion, and figure out how to actually control it when you want it. You don't always want to be going forward. Sometimes you want to turn around. Sometimes you want to stop but not actually drop back down to the ground. And sometimes you might want to actually stop before you fly off the end of the board, stop hovering. These sensors that we're going to be using in this class work on a variety of different principles, and you as a team can decide which ones work the best for you. Our playing field was designed intentionally to give you opportunities. We have some sections of the playing field that have black surfaces, others that have white surfaces, others that have silver surfaces to make life complicated. And you can use your sensors, like a light sensor, for example, pointing downwards that can detect changes in the amount of reflected light. It says, okay, I'm over the white section, I'm over the black section, I'm over the silver section. And you can decide what you want it to do. The start and finish lines are black, the middle of the field is white. Okay? And if you want to stop, maybe you say, my sensor just sees black surface, time to stop. Or maybe it's just time to turn around. Okay? We're also giving you a touch sensor. Actually, back up here. We're giving you a ultrasonic sensor, a distance sensor. It's somewhere in here. It is in the previous one. I don't have a picture, so I guess it doesn't matter. The distance sensors allow you to measure things that are up to maybe 2, maybe 3 feet away. Okay? Like the back wall. You know you're approaching the back wall because your distance sensor says there's something there. Right? You can slow down, stop when you get within 10 centimeters or 3 centimeters or whatever. We have touch sensors where it actually detects when when the sensor is being pushed in or when it's being released. Okay? You also have a timer. The timer is not technically a sensor, but you can use it to help control things. Like, for example, you know that you've crossed into the black surface turnaround zone, but you know that you're not yet all the way in. Your hovercraft's 2 feet long, right? You want to wait 2.1 seconds before you actually stop and have it reverse direction. You can use timers with the Legos, all right? It can be useful for that kind of thing. There are all sorts of third-party sensors for the Legos. If you want to use them, you can buy Geiger counters and GPSs. You can buy all sorts of stuff that work with your Legos. You need to figure out how to get it in your budget and how to use it. Okay, so let's just finish up with a couple slides here. The last clicker. How often is your team actually meeting? All right, hopefully you guys have met at least once, preferably a little bit more. Now, quick parting thoughts here. I recommend that as you do your brainstorming, you do not get too complicated. Put those complicated things on your list of ideas, but hopefully you'll figure out ways to make them more simple, because in the end, you're not just handing this off for somebody else to do, you actually have to do it. So I'll just leave it at that. We'll see you guys on Monday. Don't forget your various assignments.